Generalizing periodic Delaunay triangulations in CGAL, that is the Computational Geometry Algorithms Library. I'm Georg Osang from IST Austria, and this is joint work with Mal from Geometry Factory and Monique from INRIA. So the setting is as follows. We have an infinite point set in Euclidean space which has translational periodicity or is invariant under certain translations, and we want to find its Delaunay triangulation, which of course is also an infinite object. Of course, our input should be finitely represented, so that works as follows. We have a basis, and this defines the lattice, which is the set of integer combinations of these basis vectors. So, strictly speaking, one has to distinguish between the translation maps that are associated with these vectors and the points in Euclidean space that are associated with these vectors, and I will make use of both of these viewpoints. So furthermore, we have a set of representative points x, and the infinite periodic point set is basically all the images of x under the translations that are defined by this lattice, like this. So again, the output is strictly speaking an infinite object, but in practice what we want is a finite representation. So for each of the cells in the output, for each equivalence class of cells in the output, we want one representative. So it would kind of look like this. One caveat is that if we just label the equivalence classes of points with labels like here A, B, and C, then these triangles in this case are not uniquely described by the labels of these points. So if you look, there's two triangles in dark red, and both of them consist of the vertices A, B, and C, or the equivalence classes A, B, and C. So this is not enough. So we need to associate some additional information, but we'll talk about this later. So what is this useful for? Well, so one example is for simulations. Often one would like to simulate one object in infinite space, but in practice the closest thing that comes, that works like this is, rather than putting it in a bounded container, we put this object into, or have like an infinitely many copy of this object in all directions. Here on the left hand side you see a protein in water, and so one copy of this data set fits into a cube, and we copy these cubes in all directions and run a simulation. Sometimes, especially if, for example, this protein is rather elongated and not round, then we might want to not use a cube, but rather some more rectangular shape, just so that we have to insert fewer water molecules and save on computation time and computation cost. So this is one application. Another application is generally in crystallography. So crystals are infinite periodic structures, and here, for example, we have wollastonite, and interestingly, these translations under which it is invariant, these vectors are not even orthogonal. So it's not like a cube or a rectangle, but like a different shape of the domain in which we have the representative point set. And so this is interesting, for example, when studying pore geometry and zeolites and trying to predict physical properties of these crystals. So I just introduced the setting, then I will talk now about what is currently out there and what is currently in CGAL, then how we generalize it, mention a couple of details, and then show some experimental results. So apart from CGAL, there are, strictly speaking, some implementations already out there. So these are Voro++ and CO++. They both work in 3 dimensions, and they're basically focused on particle systems. In principle, one could put these particles into a bounded container, or one can specify periodicity in different directions. And it computes, like for each individual particle, it computes the Voronoi cell as a half-space intersection. In particular, one could query just one single particle and just get the Voronoi cell without computing everything else. This is the main application, or the main use case is getting physical parameters or statistics that are computed via, for example, the geometry of the Voronoi cell. On the other hand, like these more combinatoric, like the Delaunay combinatorics, are not so straightforward to access, and also it doesn't use exact arithmetics. It uses some trickery there. On the other hand, so in CGAL, what is there is both in 2 and 3 dimensions. However, it only covers the cubic case, which means that the basis of the lattice is the standard basis. In particular, the lattice vectors are orthogonal. On the other hand, it offers like a very flexible design. For example, via a geometry kernel, it can be specified. One can use exact arithmetics. It's possible to attach additional custom information to vertices and cells. And it also gives access to a lot of triangulation primitives. So one can iterate over all the vertices, edges, faces, and cells. And you also get adjacency and incident relations between cells. So for example, I could query which are the cells that are incident to a given vertex and enumerate those. So our goal is so that we can leverage all these features of CGAL, and also so that our class, or our implementation plays along nicely with everything else in CGAL. We would like to have it in CGAL and provide a user interface that is similar to the generic case, that basically pretends to the user that we are dealing really with an infinite periodic triangulation. So, as I just mentioned, the current implementation CGAL only covers cubic periodicity, and the underlying algorithm is the Boyer-Watson algorithm, which inserts points incrementally, and it does that by inserting them into a periodic triangulation data structure, which initially take 9, or in 3 dimension 27 copies of everything. So whenever the user inserts one point, internally there's 9 copies of the point inserted, or 27. And after a certain criterion is met, which I will explain later, then only 1 copy of everything is needed. So everything is converted to only contain 1 copy, and of course the algorithm runs much faster. So let me illustrate this. So let's say the user has inserted 1 single point so far, so the periodic triangulation data structure is inserted with is initialized with these points and this triangulation. So now when the user wants to insert another point, we have to insert 9 copies, and we do this one by one. So first the point is inserted, the conflict zone is detected. When I say conflict zone, it basically is those set of triangles or cells in 3 dimension which need to be removed and replaced with different triangles. And this is basically the way the Boyer-Watson algorithm operates. So we just inserted the first copy. So now we insert like a second copy, and then 3, 4, 5, 6, 7, 8, 9. And now we have this data structure, or now we are done inserting like the second point that the user specified. And if the user wants to insert a third point, again we insert 9 copies, and so on. And then at some point this criterion I mentioned is fulfilled, and we restrict from 9 copies to only 1 copy of everything. And from then on we just need to insert 1 single point each time the user wants to insert a new point. Okay, so how does this generalize, or how does this not generalize? So one thing that does not generalize is starting off with 9 or 27 copies initially. So imagine instead of a square domain, which is copied in all directions, we have a more rectangular domain. And here we have a triangulation which already has, I think, three points inserted, and we want to insert the fourth point, and again it has to be done one by one. So imagine the first one is being inserted here. The conflict zone now is actually very large because this domain is so elongated, and the problem is that if the conflict zone is not contractible, the Boyer-Watson algorithm doesn't work. So in this case it simply would not work. So you might ask, well, why use Boyer-Watson and not like flips to compute this triangulation? So there are two technical reasons why we don't do this. Is already in 2D the code complexity of implementing this is a bit higher, and Boyer-Watson just makes the code easier to maintain in the long run. And also in 3 dimensions it becomes even more complicated, and it's not immediately obvious that the periodic setting actually works as well. So how do we solve this problem? So there's one classic result that comes to our help by Dolbilin and Huson. And so first off, each lattice point has a Voronoi domain, so which is marked here in blue, the Voronoi domain of the origin. And so we can scale this one up. So it's scaled by a factor of 3 in every direction. And now the main result is if we take this infinite periodic point set, but we restrict it only to those points that are within this scaled domain, and we triangulate that this is basically sufficient to give us the periodic Delaunay triangulation. Of course, we see some cells on the boundary which don't look very periodic, but the result asserts that like all those cells which have at least one vertex in the Voronoi domain of the origin, those cells are good cells in the sense that they are part of the periodic triangulation. So I marked those in black. So with this, we can now outline our algorithm, which is, so we start with, you know, we start with taking like these points that are within the domain which is scaled by a factor of 3, and then insert points in there. And so basically we have a Euclidean triangulation of this restricted infinite, this point set, but restricted to the scaled domain, which means in practice like there will be 9 or 27 copies of each point inserted. And as we saw, like this triangulation has a lot of junk cells that we don't really want, so we need to make sure that to the user we provide an interface which only gives them the periodic cells and the corresponding adjacency relations and so on. Once the aforementioned criterion is fulfilled, then we operate akin to the cubic case in CGAL, which means we use a periodic triangulation data structure rather than Euclidean one with an interface, and we insert 1 copy per point that the user wants to insert. So let me illustrate this. So we compute the Voronoi domain, we compute the scale Voronoi domain. Now when the user inserts 1 point, we take all its infinite periodic copies that are within the scaled domain, so within this light blue domain. We triangulate this, and so now if the user wants to query like the set of cells or adjacency relations, we need to identify a set of representatives, which I'll talk about later, how we do this, and also need to provide the adjacency and incidence relations to the user if they request it. Now if the user inserts another point, again we take those periodic copies that are within the scaled domain, and so on. And so at some point this criterion is fulfilled, and then we can switch to a periodic triangulation data structure, and from then on we just insert 1 point each. So there's a conversion process involved, and then we just have this periodic triangulation data structure, insert 1 point at a time instead of 9 or 27 copies each time. So to give a few more details, so first off, so how do we compute the Voronoi domain of the origin? So there's a notion of reduced lattice basis. So for a lattice, the basis is not unique, but it can be reduced. There are different notions, but we choose an appropriate one. And then we can obtain the faces of this Voronoi domain from certain combinations of the basis vectors. In particular, the faces are normal to certain combinations of the basis vectors. This works at least in 2 and 3 dimensions. We only do 2 and 3 dimensional case, but if one wanted to implement this more generally, this would become a bit more complicated. It doesn't work as straightforwardly anymore. So then, how do we compute the point copy of the, if one point is inserted, how do we find the periodic copy which is inside the domain of the origin? So this is basically equivalent to solving a closest vector problem, which is generally believed to be hard. But fortunately, we are in a small constant dimension, 2 or 3. So in practice, like any of the algorithms work quite well, and so we picked one that was reasonably simple. And then, of course, we don't just want the point that is in the domain, but we want all the points that are in the scaled Voronoi domain, scaled by a factor of 3. So how do we find all the point copies that are within there? Well, it turns out we managed to show that there's a fixed set of integer combinations of these basis vectors which actually don't depend on the lattice. And if we translate these points along this fixed set of integer combinations and then check these translated points for containment, we will find all these 9 or 27 copies that are within the scaled domain. So this fixed set of combinations, in 2D there's 13 and in 3D there's 75. So now as for the output and the interface that we provide to the user, so when we have a cell that is part of the output, as I mentioned before, we need to associate some additional information because just the vertex labels are not sufficient to fully describe it. So one thing to observe is, so for one, the Voronoi domain of the origin, like if we translate it along those lattice vectors, it actually tiles the Euclidean space. And furthermore, each of these lattice vectors is an integer combination of the basis vectors. So each of the copies of this domain can be identified with a vector of integers, so which we have done here. And then each point copy that we have can be associated also one of these integer vectors, which we call offsets, by simply taking the integer vector that's associated to the translated Voronoi domain which it is contained in. So for example, the point on the left is in the Voronoi domain of the origin, so the vector associated to it is 0, 0, while the two points on the right in this triangle, they are in the Voronoi domain which is identified with the vector 1, 0, so we associate that vector with them. And that describes the cell fully. So now, of course, we have like all these triangles in this triangulation. Most of them are junk, and some of them are, okay, but we have multiple copies of different equivalence classes. So we need to find identical, representatives. So we have a nice simple criterion which basically takes the lexicographic minimum of the offsets of the vertices, and if this is 0, 0, the 0 vector, then it's a canonical representative of cells, and the same for vertices and edges. Then of course we have to provide the neighborhood relation, so there's a bit of technical stuff going on under the hood. So for example, if you want to have the neighbor of this red triangle across this edge, we can't return this triangle because this one is actually not a canonical copy, but it's it's just in this Euclidean triangulation, but rather we would have to return this one to have everything nicely consistent in our interface. Okay, so now we've talked about this. So what is this mysterious transition criterion that I've mentioned before, which somehow guarantees that we only need to use one copy of every input point and we can use our periodic triangulation data structure? So basically what it says is, if SV is the length of the shortest non-zero lattice vector, then if the circumradii of all the cells are smaller than 1/4 of this length, then all the future insertions, the conflict zones in all future insertions will be contractible, which means the Boyer-Watson algorithm will work. So in practice, this number of points until this criterion is fulfilled, so for one depends on the shape of the Voronoi domain, but also if the points are more evenly distributed, then in generally we would expect this transition to happen earlier. So we have some experiments on this, and we managed to actually establish a relationship to the shape of the Voronoi domain, which is, if we insert points randomly in random order and in random locations, then the number of points until this criterion is fulfilled and we can switch to the second phase is proportional to the volume of the domain divided by the shortest lattice vector cubed in 3 dimensions or squared in 2 dimensions. So intuitively, this means if the Voronoi domain is more elongated, we need more points. If it's more round, we need fewer points. And to note is that this is for random points and in random order. If the points were distributed more unevenly, then it might take longer than this. So we ran our code, our implementation, and compared it to the existing one. So on the right, for different input point sizes, point set sizes, so from 1 to 10 million, on the right hand side you see the runtime of our new implementation in seconds. In the middle column you see the current implementation CGAL, which is limited to the cubic case, and it turns out the performance is pretty much the same, which is good news. And interestingly, for like smaller sizes of input point sets, so like around 1,000, our algorithm is in fact even faster. And the reason for that is that it uses the Euclidean Delaunay triangulations, while the cubic case uses periodic ones. And these Euclidean ones have been quite optimized in the last 10 years, so they run much faster. You can also see this in the left-hand column. So the Euclidean case is significantly faster than the periodic cases. And interestingly, 10 years ago, if you did this comparison between the Euclidean and the cubic case, they had roughly the same runtime, but now the Euclidean case got optimized and the cubic case didn't see these optimizations. And so now, what is the runtime for different lattices? So now we compared the cubic case. What about other lattices? So one would expect that if the phase switch happens later, our algorithm would run slower, and roughly that's the case. But it seems like there's also a few other things going on. And I'll not go into any more details here, and rather just close with a short summary. So we have periodic 2D and 3D Delaunay triangulations for arbitrary lattices, not just the integer lattice, within a branch of the CGAL code base that's the current state, and we aim to integrate it into proper CGAL to get it as into a proper release. The performance is comparable to the CGAL implementation for the cubic lattice, which is good. And internally, our algorithm operates in 2 phases. However, to the user, we provide a uniform interface which pretends to the user they're always dealing with a periodic triangulation, and the internals are hidden from the user. So they can just access the periodic triangulation, the equivalence classes, adjacency relations, and incidence relations. Thank you, and if you have any questions, please ask.